Okay, so before our second break, forgot to record the video. Forgot to start the recording for the second part, but we went over a queue back and forth. That one's kind of a mess. But we saw linked lists and then stacks and queues, which are when we talk about them like nouns, but in a lot of ways, it's more like a verb. A stack and a queue is how we process the data in a list. I'm going to go ahead and erase this as we move on to the next one. So stacks and queues are still kind of built out of a list. We start with a list and then start doing things with it. Oh, actually, this one that I just erased, that doubly linked list, it's a whole lot easier to make a queue out of that, because then we can start at the end and come backwards, or we can go both ways, so we don't have to make adjustments like we did there. So the next one after a linked list, primary sort of structures, like maybe that's not the best way to do it. And that would be a tree. We've already seen tree diagrams. When we did object-oriented stuff, we put together a tree diagram, looks something like this. And we might have 3 branches on this one. And this one has 1 branch and 2 branches here. And we just build up this big hierarchical structure, some sort of root element, and then our root, and then the next ones out are branches. And when we get to the end where there's no more branches coming off of it, that's going to be a leaf. So that is our actual terminology for a tree. The one we really care about, though, is what's called a binary search tree. Which may not seem like it at first glance, but the definition is in the name of that one. It is very specific. So a special version of tree which a tree is sort of a hierarchical structure with the root and then all the child elements coming off of it. So our directory structure on our computer, where we organize all our files and folders. Websites would often be organized in this sort of structure. Lots of places it gets used. But a binary search tree is a special type of tree where each node has at most 2 branches. Each node has at most 2 branches. And I'm going to put in parentheses down. So as we go down the tree, we're only going to split off. Any particular node can only split 2 times. And a left to right ordering. So it's a tree, binary, only 2 branches, and left to right ordering for horizontal. Maybe I should put vertical and horizontal there. Instead of down, I'll put vertical, because we can go back up a tree. And horizontal gives us left to right out ordering. So what I'm going to say for our example is smaller things to the left, bigger things to the right. That's how we always draw a number line, right? Draw a number line, smaller things to the left, bigger things to the right. And left and right, that gives us 2 nice little distinct names that we can organize stuff off of. And it's a binary tree. Each branch has at most 2 branches. So that's the 2 lines that come off. We have a left and a right line. So this one I drew is not a binary tree because we have 3 branches on this one, on that one. So that's just a regular tree. If I erase this branch, now it's a binary tree. So we have left and right. If we go right, then there's a left and a right. So we can go left, then we have left and right again. So there's our organization for the tree. These can get sometimes stacks and queues were for minimizing RAM usage. This is for maximizing CPU speed. So this is fast. Great big, all capital letters, bunch of exclamation marks. This is fast. So while stacks and queues are where we optimize our RAM usage, a binary search tree is where we get speed if that's what we want. Sorry, I forgot to ask if it's okay if I erase this. That was an arbitrary picture, but we're gonna getting ready to draw more. I forgot to ask before erasing it, but the key points is our initial element is called the root, and then we'll come down those left and right branches. And if there's another node there, then it's a branch. But if that's the last node going down that pathway, then it's called a leaf. The end of a branch. That's the terminology for it. Typically, they use recursion, but we're just going to use while loop because we haven't really seen those. And the big thing is we have 3 ways to traverse. 3 ways to traverse the tree. And that's where part of the speed issues come from. So let's make up an example here. Let's say we have a 7, an 11, 3, 5, a 19, a 24, a 32, and an 8. There's our data set, some integers. So we'll just start putting these in here. So our first one's going to be our root. So the root element's a 7. I don't really have too many colors. I'll put this on this. So here, smaller to the left, bigger to the right. So we can have at most 2 branches off that 7. Our next element's an 11. Where's that going to go? Left or right? Somebody want to shout it out? Somebody on the Zoom call? Tanae pointed it out, but I don't think they can see you on the camera.
Would it be left?
Yes. Oh, wait. Actually, no. Our next element's an 11.
Okay. Making sure. I was making sure. Yeah, it would go to the right.
Yeah, so bigger things to the right. Now a 3. So we always start back at the root. We going left or right? Samantha put it in the chat room. Thank you. A 3 to the left. So we go back to the root. So starting at 7, which way do we go? Left or right? Somebody on the Zoom call? I saw somebody unmute.
Still to the left, right?
Yes.
I mean, correct.
Yeah. So 5. We go left, and now we're at 3. We go back
then to the right.
Yeah. 19. Which way are we going to go? Yeah, Tanae's pointed. We need to go right to 11 and then right again to a 19. I'm trying to space this out because I'm going to draw 3 lines around this picture. 24. We're going to keep going right? It's bigger than a 7, so we go right. Bigger than 11, go right. Bigger than 19, so we go more right.
Same thing with the next.
I need to change this or we're not going to be able to see this. I'm sorry. Let's make this a 14. So we go right, right, and then left. A 14, then 32 is where we go here.
Can't we just go left on 11?
No, because 14 is bigger than 11. So we have to go to the
Yes,
right.
sorry.
Yeah, so bigger things to the right. So we go right until we hit something bigger and then we go left again. And we keep going until we hit the end of the list. Oh, excuse me for a second. Hey, Skip. Marlene just sent out an email. She's with this 279 course, the state workshop. She sent an email to me and you. She's not it in years. And, she's not able to get this next. Get problems like that. Which says, see if there's any back. She said, no, she doesn't give it to them. They schedule it. Sorry. Personally. Okay, you might want to check her email. It just came out a few minutes ago, so. But yeah, I'm not sure exactly what's going on with it. I just saw it a moment ago. Oh, and 2 more. So now 8. We go left and right, and then right again. Does that structure make sense? I'm going to add one more thing in here. Let's add a 2. And that should get us the pattern, yeah. Need to have a certain amount written there so we can see the pattern. So we have 3 ways to traverse our list. The first one is in order. I'll do that in red. In order. Am I still on the video? Yeah, okay, good. So we always start at the root. And in order is left, node, right. And as we write these out, please commit these to memory. These are going to be very, very important as you progress forward from here. They show up in lots and lots of places. We need to know what in order, pre-order, and post-order are. So in order, we go left as far as we can. Then we come back and get the node that we passed, and then we go to the right. So we always start at the root. So we'll come in, and now we go left as far as we can. We can go left, and go left further. Then we want to grab our left one. Left, node, right. Now we just keep following this path as we go over. We'll come back up. Node. So left, node, right. And notice how we're picking it up in order, 2, 3, 5. So it's basically sorting our things. Well, we went left node, right, and every time we hit a node, we have to start over again. I kind of just went past that to fill it in, but every time we hit a node, we start over. So left, then we start over. Can we go left further? Yeah, go left. We can't go left any further, so then we go node. And well, we just came from the left, so we already have what's to the left. So we grab the node. Then right. Now that we've done this, we need to start over. Left, we can't go left. We already have the node. So the only thing left is only thing we can do is go to the right again. Well, then we come back around. That's left node right. left node right, come back around. We can't go any further to the left. So we come back around. Oh, we got a node. So left node right again. Oh wait, I put the 8 in at the wrong spot, didn't I? Sorry, 8 is bigger than 7. Let me use my fingers or something. 8 is bigger than 7, so it goes to the right and then the left. Okay, so now we go left node right. Can't go left. We already did all those, so all we can do is come back around. And that brings us back to another node. 2, 3, 5, 7. Well, can't go left anymore. We already did all the left that we could handle from that node, or that existed, so we go to the right. We get to this node, we have to start again. Well, we can't go left, so let's go left, node, right. And that's how we're passing through this. Well, we get to a new node, we got to start over. 19, we can go to the left. So let's go left, node, right. And notice the order we get there. We go left all the way. We got 2, 3, 5, 7, 8, 11, 14, 19, 13. So we put all of our elements in order. 2, 3, 5, 7, 8, 11, 14, 19, 32. All right. Next one I'll do in blue. Pre-order. Because we don't necessarily have to go in order. That's not always the most useful way to do this. You can also go pre-order. And the prefix goes where the node is. So with pre-order, we go node left, right. Node left, right. And I'll go ahead and write post order up here. I only have 3 markers with me. Somebody said they have trouble seeing green, so 3 markers. So the last one will be in black. Post order. We go left, right, node. So you see the node is what dictates that prefix, if that helps you remember it. In pre, node is first, and in post, node is last. And in order, node comes right in the middle. So let's see what happens if we go this pre-order one. So got my blue pen, we want to go node, then we go left, then we go right. So as we come in, oh, we hit a node. We're gonna grab our node. Now we go left as far as we can. Or actually we have to keep grabbing things along the way.
Left, right, would be go from 3 to 5.
Yes. We go left, so we start over at every node. So we hit a node, so we start back over at the beginning node. Now we can go left again. Go left. Oh, hit a node, so we grab that. Can't go left anymore, so now we go back to the right. We already grabbed the 3. So we grab the go right, and we can hit a node. Can't go left. All we can do is continue to the right. We already grabbed the 7. As we come back around, we hit a node. So we need to grab that 11. Hopefully those dots are showing up on the picture. Kind of see the order that we're getting them in.
You can zoom in.
Node. So now we go left and we hit a node. Only thing we're left to do is go to the right. So we go right, we hit this node, left, right. Then we have all our elements again. In a different order than we got the first time. Which I think I got that set up so that we can see, hopefully see the order a little bit. 7, 3, 2. So we start going down. Then we come back up. 5. Oh, I didn't quite get enough. After the 5, we come around to an 11. Then 8. We go back. If we ignore the 5 there, so we get big and then we go down. Then we go back up. If there was things after the 5, like a 6, a 7, we'd hit those along the way. Then go back up. 11, 8. So we go back up and come down. After that, we go 19, then 14. So we go up and come down, then 32. Hopefully that's enough to see the order. So with this one, I'll draw a picture like this. We start upward, we start at a high value, and then we go down. Then we jump back up and come down. Come back, maybe that should be a dotted line. So we pick something in the middle. It doesn't have to be the highest or lowest, but we walk downward a few values. And then we come back to a high spot and walk downward to a few values. Then we come back up to a high spot and walk downward to a few values. And we traverse our list this way, like a wave going through it, instead of right in order. Because sometimes this is a better way to search things. It breaks it into sections, right? We have the ups and downs, and we're going through it in a different, sort of a different order. Hopefully that makes sense. And then post order is sort of the opposite of pre-order. We go left, right, left as far as we can, then we come back to the right, and then we grab our node last. So we come in, same place, go left as far as we can. Can't go any further to the left, so we'll grab the 2. Then we want to go as far as we can to the right, and then we come back and grab the node. So we'll pass the node, grab the 5. That's as far as we can go from the right. And now we'll come back and grab that 3. So to the left, as far as we can go, to the right, as far as we can go, and then come back and grab the node. Well, that's a node, so that's all of the left. So now we need to go to the right. Start going to the right. We hit this node, but we need to go as far as we can to the left first. So we'll come over here and grab the 8. That's as far as we can go. Then we need to go as far as we can to the right. So we pass the 11, pass the node, come back down, grab that 19. Or, sorry, we're starting to the right. We pass the 11. We see the 19, but we can go left again. So we go left as far as we can go to the left. And we grab this first. Get our 14. We haven't grabbed the 19 yet. We passed both the 11 and the 19 after the 8. Hopefully these pictures aren't good. Hopefully that's making sense, because that picture is definitely getting cluttered, isn't it? As far left as we can go gives us the 14. So now we come back as far right as we can go. And now we come back and get the nodes. So then 19, 11, and then 7. So when we list this in order, we came around, grabbed our 2, then the 5, and then the 3. And hopefully from that previous wave-like motion, you can figure out what's going down here, especially since our first one's a 2. Kind of going in the other direction. 5, 3. Then we came all the way around, got an 8. Came around 14. 32. 19, 11, 7. I used to order, it's kind of hard to see it in a couple places that 19s, those are all independent, but we start small and then this time we go up. And then we jump back to some small value where we'll walk up again. Jump back and kind of go up a few values. I had to choose a small enough number that would fit on the board and try to show the pattern. Then we go up. So see, this one, we're just traversing in order. We started our smallest value and then just go up the whole time, which isn't the most efficient way to walk through the list, right? Because really what the value we're looking for, if we want the smallest element, that in order will work fine. Some things in the middle, we could get to quicker if we jumped around instead of going straight through the whole list the whole time. The highest value we could definitely get to quicker if we jump around instead of going through there. But pre-order gives us a way to traverse the list where we start at a high value, walk down, then jump it up to high value and come back down. Up to high value, come back down, and it's like a wave going through there. And then post-order kind of flips the order and we go the other way. We start at a low value and then we go up. Start at low value, go up, low value and go up. And basically, to write this, I'm just going to do a very quick version. Those bare minimum ones. Let's say a binary search tree. Oops. You're looking at something on the board. Got it. There we go. I'll make a new class called my BST. Or let's spell binary search tree out the whole way. So we'll define our init. Init is self, and we need to know what the root is of the tree. So we can't have a tree without a root. So I'm going to put a root element in here. That's the first thing we pass in. Everything else we'll add to the list afterwards. We'll need a couple parameters. We need actually I'm going to do element again. That way it's closer to the list. We'll just keep track of what the root is manually. We don't necessarily need to label it a root in the code. We have the element, the node, and then we have a branch going to the left and a branch going to the right. So self.element is that one we pass in. Self.left starts at none. Self.right again starts at none. And then when we add something to the tree, that's where we build our tree. Smaller things to the left, bigger things to the right. So our add method will have self and then the element we want to add. I'll abbreviate it here. So L. So I should probably make a note. That might make everything easier. I'm going to change this a little bit. I'm going to make two objects and I'll just make a node that is just those three things. And then we'll make a tree that combines them. This is just going to look cleaner. My BST. And then when we do the constructor here, self, and then we'll pass in one of those nodes to make a tree. So everything we pass in I'll call it node. Because it's gonna have an element and a left and a right branch. So we just want to make sure that we pass in a my node every single time. So self dot node equals node. This is going to make it cleaner. And then we have a left and a right. So yeah, we'll add that in, and then we can do an add method to this. Define, add something to our tree, which will need the self, and then the new node that we want to add, or new element. Probably easier to add an element at this point. Or you can just add nodes all the way through. Let's add a node. And then we just need to check the stuff in that element. So each element has a node, or the element itself. Each node has an element, then the left and the right branch. So somewhere we're going to have a root. We need to say what our starting root is. Which that's what I was going to rename this. I'm just going to call this root. That'll make that a lot easier. Self.root equals that root that we pass in. Then we'll add a node. So what we want to do is go to self.root. Compare that to self.root, which will be a node. This needs to be a my node object. So that we have the element left and right. So then we can compare it. So if node.element, the one we just passed in, is less than root.element, oh, sorry, self.root.element, which way do we go if it's smaller? The question from 10 minutes ago. The binary search tree, if it's smaller, which way do we go? Yes, go to the left. So then we want to go, want to go to the left, but we don't know how far to the left we can go. So we need to do this recursively. So what we'll do is call the add method. If node dot is this the way I want to do it? Yes. Again, there's lots of ways to do this. So some of them are cleaner than others. Maybe I just want to do, I'm going to switch this back to just having a node instead of the root overall. Node. And we'll pass it in because this will look a lot better. We'll just pass in the root. Whoops. That's what I did. So root and node are both elements, are both nodes. So we'll compare them. And we'll just pass it in every time. This is going to make things look a lot cleaner. And it's been a long night, so we probably want clean looking code at this point. We'll pass both of them in. If the new node we're adding is smaller, we'll go to the left. And well, we need a new small section. So like here on this picture, if we go to the left, there's 3 elements, right? So that could be taken as a smaller subtree. So the next element down the left branch should be If no dot element is less than that, we go to the left. So we'll go, whoops, my cursor went somewhere else for a second. Root dot left, and then we're still checking the same node. So we go down that left pointer, and we'll keep going until we find the empty one. So we should probably first off check if root dot left is empty. There we go. Go back to before I push the wrong button there. If node's smaller, we need to go to the left. If root dot left is none, then we found the end, right? If there's not anything there and we need to go to the left, then we will, well, we'll just put it in there. Then root dot left equals node. And again, we'll return. But if we don't get all the way to the end, right? If we don't reach the end branch, the leaf, then we'll just recursively call this same method. And whoops, I can highlight greatly. Then we'll treat the next element to the left like a new root and keep going as far as we can. Because if it's not to the left, could be the other way, right? If node dot element is bigger than root dot element, what way are we going? We go right this time, right? I'll come back into the if statement. So if it's bigger, then we need to go to the right. So we'll call that add method recursively with root dot right as a new root and still looking at the same node. Otherwise, we'll do the same check. So if root dot right is equal to none, then we want to set root dot right equal to that node. We got all the way as far right as we can go. We know we're going to need to go to the right, and there's an empty spot. That's where this one pops in. Otherwise, we go further to the right and treat the next branch to the right as a new root when it comes back around recursively through this call. Oh, then we can return. And return when we're done. We also have equality, right? But did our definition say anything about equals? We don't want duplicates. So this also cleans up duplicate data. Duplicate data. That was hard to say for some reason. It cleans up our duplicates. So we don't need to worry about if it's equal. We just want to put things to the left or the right. And if we get the same number coming in twice, we don't need to store it in our tree twice because that's going to mess up our whole pattern. So I need to copy these over. We got these. Cut that, put that in our test case. Copy that divider. And import that. We'll write this in a second because all we could really is add some stuff to the tree. Probably one way to see it. Well, we can add some stuff. Make sure we don't get any crashes when we add stuff. So we need a New binary search tree, and we set up our root. So let's make up a list. Let's use the same list that's on the board. 711.3, 711.3, 519.14, 32.82. That'll make a good test case because we already have the answer written on the board, so that'll make it easier to debug instead of trying to come up with, figure out what all the orders are for another one we listed. So we want to create a new binary search tree and pass in a node to serve as our root. So tree is my BST, and then what we want to do is we need to create a new node with an element. Must have got kicked off. I think that's happened a couple times. I have a bad internet connection. So then here, we're passing a my node thing with a 7 to be the element. And then we can start adding stuff. There we go. I've done this enough times. I knew when as soon as my cursor went to the wrong spot when I hit enter, I knew the indentation had gotten off. It hadn't marked the indentation error or anything, but the cursor would have gone to an indented spot otherwise. Now we can add stuff. So like tree.add an 11, tree.add a 3, tree.add 5, tree.add 19, tree.add 14. So as you can see, we would probably put this in a list and just pass it into a function that adds a whole bunch, adds a list all at once recursively. You all know how to write a for loop. 32, tree.add an 8, and tree.add a 2. We can check and make sure we don't get any crashes so far. Oh, take 0 positional arguments, but 1 was given. Do we not do that? Oh, whoops, this should be the keyword class. Sorry, it's an object, not a function. That one is definitely just from it's getting late. Oh, we have to put the root, don't we? And every time the root is this or tree. This is why I wasn't going to do that at first, because we need to put tree as our root every time. Which looks a little bit odd. We saw earlier we could have used that self parameter, but when we have the recursive call, we can only use the self parameter on the first one, and then we have to adjust it as we go deeper. Does everybody see what's going on there? Our add method has a root. We have to know what the root is every time, and then the node we want to add. And our root is always the tree, or this variable refers to the tree root. So we just keep passing that in as the node, and then we add things left and right. And I expected it to work that time. What didn't it do? End object has no attribute element. Oh, and then those should all be nodes. Sorry. That one is just getting late. Let me Let me copy this. Our second parameter is my node within 11. Get rid of all these. Highlight that, copy, paste, paste, paste. Whoops. Paste, paste, paste. So what do we got? 11, 7, 11, 3, 5, 19. Where parentheses go? Oh. That's not good. I don't know where answer key is on this one. Okay, somehow I'm in an insert mode. And I don't know where that's at on this keyboard. So I'll fix that later. We have a 1914. You can also just fix it this way. 32. An 8. Oops. An 8. Oh, I don't like insert mode. There it is. It's on this. It's on the number pad. Okay. I really dislike the overwrite mode. It gets very confusing when it doesn't just when it gets rid of the text that's there. So paste in one more for a 2. Sorry, that was odd. There's our adding stuff in. Notice it's very repetitive. And why did that crash? My VSD object has no attribute element. I have to type tree.element here. $164. So let's see if it goes one line. Oh, not node. Oh, has an element. We'll go one further this way. Okay, so I am getting tired here. 165. So it went one line further. So we need to type dot node on each one of those. I always dread this day in class because it's so much looking at code. When we get down to the end, we get silly mistakes. Okay, I'm going to pause there for a second and wipe my eyes. And now let's talk about what was going wrong there. So it's not the tree that we want. We want the root of the tree. So I think at one point I was thinking about calling that root and then changed it. So that's what we compare to every time. But then during our recursive call, we keep adding it. So it should add all those elements now. So we got through with no error messages. That's progress. But now we have to do our traversals. Well, I'll do them in the order we did here. So first off is in order. We need to know, well, obviously we need the self parameter. Where do we start at? And, oh, well, we just need to know where we start at for in order. So we want to go left as far as we can. So if root dot left is not none, that means we can go further, right? We go in order, call in order again, whoops, sorry. Call self dot in order with root dot left. If, oh, sorry, elif, root dot left if root dot left is none, then we've gone as far left as we can, right? Can't go any further to the left. That's where we want to print it out. Just the way I want to do this. Root dot left is not none. We go further to the left. If it is left, it is none, then we print whatever it is. Root dot element. We've gone as far to the left as we can. You know what? I'm at the point now, I'm going to start making silly mistakes. So I'm just copying from last year's example. I'm going to open GitHub and copy from last year's example, and we'll talk about it instead of typing it. I've been here since 8:30 this morning, and it started the day with a meeting that went to 12:30. So I've been staring at screens for a long, long time today. I think my eyes have hit the limit of staring at screens for today. So I'm going to go back to the spring 2023 version of this class. Open the data structures. So the last time I taught this in Python. Oh, here's a binary search tree right here. So the node looks about the same. I gave it different names, called it value. Use insert instead of add, but that's the same thing, right? Same thing we just did in the add method. And we have this. If root is not none, we call in order with the left. Okay, that's a lot cleaner than what I was trying to type here. Let's go back to this version from last year. I'm going to copy that, and then we'll just talk about the code. Oh, okay. If root is not none, we go further left. If the root is none, right, so it's root dot left from the previous one, then we print it. But if neither one of those work, we'll go in order again. It looks very concise, right? Almost too concise. It looks like something's missing. So I'm going to put this in here so y'all can stare at this code. Oops, doesn't need end in it. Which I'm just going to do this. I'm going to home. Get rid of all this. Oh, why did I do that? Enter. There we go. Home. Get rid of all this. Enter. And this needs to be self.in. Self.in. Because last year I also did it without that. As last year, I didn't do it as a class. We put a class there and then everything else was just a function. That's why it was in a different class. Or a different file than the other ones. But it's no trouble to kind of put those in there. It'll be confusing at this point if I went back and just copy this. So we can talk about this code. Let's see if this works. So we need to call in order with our root element. So once we get those, we'll say tree.inOrder with our root, which is tree.node. Probably should have called it tree.root. Let that mess up. Oh, has no object value, so this should be element this semester. There we go. So notice how it came in order. Same order we have here, or well, in order we can easily see. 2, 3, 5, 7. That works a lot better just copying it because I've been, yeah, it's getting late. I'm gonna make silly mistakes or overcomplicate it. Let's copy pre-order the same way. And look how easy it is to set up that pre-order thing. Enter, come back out, paste that. All of this now needs indented one layer over. Root, passing that in, so we need self because apparently last year I didn't do it as an object itself, just did it as some methods. So if root is not none, pre-order. So we go node left, right. So we print first, then we go to the left, and then we come back and go to the right. This should be element. And then both of these are self dot. Does that do you see how what we talked about corresponds to that? Which actually we can just copy this now. Copy that. Come down here, paste that, and change this to post order. Post order, again, got self and root. If root's not none, post order goes last. Cut that. And what the prefix post always means, put it down there at the end. And change these calls to, we'll go post order, left as far as we can. Then we go right, and then we print the note. Pre-order. Start with the same root. And tree.post order. Tree.same root. And probably need to space those out a little bit. So I'll just print a couple line breaks between them. Okay. Does anybody have any questions about those? Do those kind of make sense? This day is always too long, and we have to get at least this far because of our major learning objectives. There we go. See how we got our same order here. We start at some high value, larger value, and then we walk down. I'm gonna skip over the 5 because there's nothing else there, but then we go back to a larger value and go down. So there's that wave on the pre-order one. I guess we could put some labels in here, couldn't we? Print in order. Then after a couple lines, and pre-order and post-order. That way we can see what's going on. So start at a large value and then walk down. And we're jumping around the list because if we need something that's way down here at the end, that's a lot of processing to get there if we have to do it that way every time. And the search part kind of implies it's more intelligent than just a find feature, right? So an in order is like Control F, whereas pre-order and post-order start to give us the fuzzy finder things. Get something close, and we jump around our list, not necessarily in numerical order, but it gives us a different order that might make it easier to find things. So this one we start small and then go up. Then we go back to a small value and go up. 19's out of the rest of them are out of order because they're all singles. Going back up at the end, we just grabbed all the ones we had left over. But a different way of going through the list, different orders that will be important for you later on. It's really hard to see in class. On Thursday, we're going to do Wednesday. Yes, thank you. On Wednesday, we're going to do another example where it's not a generic stack. Like we're going to make an employee object. This is a payroll calculator is a nice easy one. We'll make an employee object, and then along with like the name and address, rate of pay that every employee has, we'll just add an X field, and then we have a list. And then we'll add a pop method, or push and a pop method, in order to like process payroll, which will be coming from a CSV file. We'll just make up hours, put them in a CSV file, and then we'll read in that number, process through it. We'll also look at the next step in Django. We'll also quickly talk about some more tree stuff. I at least want to talk about a heap. Like it's this much, so it's a big one paragraph and two little pictures on the board. So that's like 5 minutes, 10 minutes, and then talk about hashing, which again is one paragraph and two little pictures on the board, which could probably be fit in there tonight, but we've been at this for a long, long time, right? So those last two minimum things, and I have a bunch of other stuff that we could go over, but heaps are really, really good for a computer. Those are important. And hashing, that has made it into that's made it into our common language, right? With hashtags. People who know absolutely nothing about computers know what a hashtag is. So I at least want to talk about what it is. A paragraph and a picture, but we could fit it in there in the next 10 minutes. It's not much on either one. But that was a lot. These are the three that are our major learning objectives. So we got through those three major learning objectives. We go to Ivy Learning. That in the syllabus. And remember, in all of your classes, you always want to look back at the major learning objectives, the things you're supposed to learn. But one of these, oh, there we go. Implement stacks, queues, and binary search trees. We made it through there, so it's the one we had to see how to implement, and we'll redo implement in a in situ manner, like in an actual situation, so we see how that would be useful instead of trying to make a generic stack or a generic queue. That's always a long night. That's why I mentioned it way back on day one. Has my camera been on all night? I didn't realize that camera was on. I'm not sure when I bumped the button. Let's put the stuff on GitHub because y'all are going to want to look at that. Everything's saved here. Yeah, looks like all the files are saved. I'll close Spider to make sure. Wednesday will be much shorter. Next week will also be much shorter because we're getting very near the end. Go to where these are. Delete the examples. There's the Git folders. So let me start PowerShell. And drag and drop thing, but I'm used to doing it this way. I'll add the stage of stuff. Commit to our changes. Data structures. Push back to the remote repository. All right, that stuff's on GitHub now, so you can go look at those examples. Probably not right now. Right? We just stared at the screen for a very long period of time. This was the longest night. There's not really a good way to split that up and do it on different nights, and those three, they're called out explicitly in our course objectives. All the other 200 level classes just say cover data structures, but for this class, it actually says stacks, queues, and binary search trees. Anybody have any questions about those? Probably not, especially not at this time. It's one of those things. It'll be a little while before you see the usefulness in that. They are very, very, very important moving forward. I can say that, but right now you just kind of have to you'll have to just take my word for it because they're not all of that in anything that would fit reasonably in classroom time constraints. So much further down the road, you're going to look back and be like, oh, that's what he meant when he said they were important. But that's a ways out in your careers. All right, that was a long night. Wednesday will be shorter. And then next week's module 7. So I'm intending for that to be pretty short because you all have projects and past due homework and all sorts of stuff to do at the end of the semester, right? So the rest of our lectures are going to be short. The tentative plan has our longest night being to 8:20. So that leaves us much shorter classes the remaining 5 classes. Otherwise, I'll see y'all Wednesday and we'll get back in and we'll pick up from there. I already said what's happening Wednesday. Y'all have a good one. See you Wednesday. Been a very long day.